networks, indeed. What I would like to convince you is what that guy said over there, really, that there are networks everywhere, and they do matter. He forgot to say that. So let's see, how do we know that they matter? First of all, where are they? Where are these networks that I'm going to spend the next 45 minutes talking about? And there, there are your communication network, right? So this is how you communicate. What you see here is the map of the internet, how the routers connected to each other, and this is how you send the message. You're somewhere here, you send the message, and ends up somewhere down there. So pretty much all of our communication depends on very, very complicated technological networks. And of course, there is Facebook, right? So what you see here is the map of Facebook users around the world, as an intern actually at Facebook put it together. And there's lots of stories to be told about the network here. It's about 800 million users back then, now many more. And what it shows is who is connected to whom. And what you see is that most of your connections are local, right? Most of your friends are actually living next door, going to the same school, the same university, working nearby. But then we all have a couple of links that takes us across the ocean and span continents. This map is interesting of its own about where the Facebook is not there. Why is it missing here? Why is it missing here? Why is it missing there? Why are there no networks, at least that we could see there? And there are stories to be told about that as well. But most important, your very biological existence depends on networks. What you see here is the network within each of your cells, how your proteins connect to each other, how they come together to form machineries that eventually do much of the work that your cells need to do to keep you alive. So nodes are proteins, and links are the interactions between them. And our very biological existence depends on these networks working right. In the moment one of these networks, one of these nodes breaks, that's a disease. And we need to understand these networks to be able to cure those diseases. So this is on the tiny level within each of your cells. And then we can also look at the universe as a network of how galaxies connect to each other, like by gravitational forces and other influences on each other. And astronomers and astrophysicists are increasingly talking about the cosmic web. That is, what are the dependencies between the different galaxies? How do we perceive as a network, and what does it really mean? So I gave you lots of examples of networks. The question is really, how do we approach them? Because in one, the nodes are molecules, and the other one is one of you. In the third network, it's a galaxy. The links could be whom you know, who your friends are, could be chemical reactions, or could eventually be gravitational forces between the individuals. So the question is really, how do we think about these networks that are inevitably around us, that define us, that really help us exist in the first place? So really what this talk is going to be about is to give you a language, give you a way to see the networks, give you a sense of what matters and what doesn't, and how do we view the world from a network perspective. Now, when it comes to network science, and yes, there is such a thing as network science. I'm officially a professor of network science. That's my job. So by virtue of my job, I validate the fact that there is such a thing, right? So the question is, the best known thing that everybody heard about in a way or the other is one important property of networks, which is the 6 degrees of separation, right? So it's a very simple claim, right? If you pick two individuals somewhere on the globe, like Sarah and Peter, Sarah may not know Peter, but Sarah knows Ralph. Ralph knows Jane. Jane knows Peter, and they're about 3 handshakes from each other. Now, this sounds cool. It's a very old concept. First time it was ever mentioned by 1929 by Frigyes Karinthy, who is a writer actually back in the country where I live right now in Budapest in Hungary. And he was the one who wrote a fantastic short story saying, we think the universe to be so big, but really it's tiny. because I'm so close to just about anyone. And then to demonstrate it, he showed how he could connect himself to someone who was really far from his perspective in 1929, which was a worker in Ford's factories. And he said, you know, the worker in the Ford's factory may be so far away from me here in Budapest, but he probably knows his manager, and his manager knows Ford. Ford knows an industrialist who has Hungarian origins, who happens to be a friend of my friend, and there we are about 4 handshakes away from each other. So you know, effectively, the 6 degrees of separation claims that you can pick any 2 individuals on Earth, and there will be a short path of it. It's fantastic, it's magical, it's completely useless. And the reason it's useless is because you don't know where that path is, right? You may know who your friends are, but you have no idea who your friends' friends are, right? So at the end of the day, you know, there may be a 2 or 3 path from you to the President of the United States, present or future, whatever it is, but if you don't know how to get there, you know, you won't be able to utilize that path. And you won't know how to get there unless you have a complete map of the network you're part of, right? And we don't. We don't have that map for social networks. We don't have that map for many other networks that we care about. So 6 degrees is still important because it tells us that in these networks we're very close to each other. And it's not only a property of the social network, it's a property of the World Wide Web, it's a property of the cell. In any large network, you pick 2 nodes and you will find a very short path to each other. So there's nothing really magical about that. And we'll see that actually this emerges even in networks that are completely randomly connected to each other. So the challenge for us is the following. You're given a big network. How would you analyze it? How would you think about it? How would you speak about it? And that language really came from the 1950s and 60s from the work of 2 Hungarian mathematicians, Paul Erdős and Alfred Rényi. Some of you may have heard of Paul Erdős. He was this very charismatic mathematician who genuinely lived out of a suitcase. He was a traveling mathematician. He would show up at some other mathematician's house anywhere in the world. He would knock on the door, and when they opened the door, he would say, "My brain is open. Let's prove some theorems." And he would stay about 4 or 5 days, which is about the time the family could really live with him. Because he would wake up at 5 o'clock in the morning, and he would start making noises in the kitchen, like really banging noises, so that finally his friend would wake up and start proving some theorems. So through his this lifestyle, actually, he ended up becoming the most connected mathematicians in the sense that he collaborated with about 500 other individuals, other mathematicians, which is very rare in mathematics because much of mathematical work is done individually by mathematicians and not in collaboration. So one of his collaborations was to his fellow, Alfred Rényi, and in 1959, they wrote first 1 paper and eventually a series of 8 papers where they started thinking first, how would large complex networks look like? And in the first paper, they even motivated what they're thinking about. They thought about biological networks as well as transportation networks. And they said, if you look at these large networks around us, they're so complicated. They look random, right? You don't know who is connected to whom. It's really hard to guess. So they said, let's go ahead and assume that they are random. And because from a mathematician's perspective, a network is a very simple concept. It's just nodes and links connecting the nodes. But the challenge is how do we place those links? And let's assume that those links are truly placed randomly. That we randomly meet people and become friends with each other, right? The molecules randomly react with each other. So they said, the way to do that, for example, is to start with a bunch of nodes, what you see over there, and you start randomly connecting with each other, which means that you pick 2 of them and you throw a dice, and if you get a 6, you put a link between them. If you don't get a 6, you're out of luck and you try again for another pair of nodes. So if you do that, you will end up with a network like that, right? Some nodes end up being connected, some don't get connected. And because I use the dice to decide that, the nodes get connected with probability 1/6, right? Because it's, every time I give a 6, I will make a connection there. So the question is, and this is what Erdős and Rényi asked in 1959, is that what happens if I start changing this P? That is the probability that two people are connected, that two molecules are connected. But I assume that still randomness rules my network. And this is what they actually saw. So if P is 0, then everybody is disconnected, right? Because I'm not succeeding to connect anyone. So I have a bunch of disconnected individuals. None of you know each other, right? You're all strangers. But when you start increasing P, some of you are becoming friends because I'm giving you links between among you. And then you will start seeing small clusters of individuals. And the important discovery of Erdős and Rényi, what they showed mathematically, is that first you have all these isolated islands, and there will come this magic moment, it's about here, when all these islands suddenly merge, and something that you would recognize as a network will emerge. So let me just kind of tell you what this really means. So their claim was that the networks don't emerge gradually, but they emerge suddenly. That is, they emerge to what we call a phase transition. So let me put it in simple perspective. All of us are told by the smarter individuals that in order to succeed in life, we must network, right? That we must make friends, we must make acquaintances, we have to know the right people. And what Erdős and Rényi said is that if you start with a group of people like you guys here, where no one knows anyone else initially, and you start networking, at first, there doesn't seem to be any consequences of that because you're just forming local cliques of people that are otherwise disconnected from each other. So there's no way that information can get from one to the other one who's in a different part of the room. But what Erdős and Rényi has shown is that as you keep doing that, there will come a magic moment when suddenly all of these little pairs will connect and you will all become part of the same network. That it is not like you network more and there will be more and more of a network. For a while, there will be it seems that your work is wasted. And there will come this magic moment where suddenly, as a transition, you will go from many isolated groups to one big community where there's a path from anyone to everyone else in the network. So what they showed really is that the emergence of the network is not a gradual process. It's a sudden process. So once we believe that, they also made another prediction that will be important for us. They said, let's ask how many links each of you will have at the end of this cocktail party as you're making friends, right? And some of you will not be so lucky, right? They will just make you talk with one individual and you end up with only one friend, right? Others will be much luckier. But if I have a large room like that, how do I characterize a more lucky and less lucky person? Well, the way to do that is to count for each of you how many friends you made, and do what we call a degree distribution. Your degree is simply how many friends you have. 4, degree 2, degree 1. And the distribution of that is simply counting how many of you have degree 1, how many have 10, and how many you may have made 100 friends tonight. And you could, because there's far more people than 100 here. So what they showed is that at the end of the night, no matter how good the cocktail is, if you are randomly making friends, your degree distribution will follow what we call a Poisson distribution, or a bell curve, or a Gaussian, if you would like. It's the same family, which means that the vast majority of you will have roughly the same number of friends, and it will be very, very difficult to find someone who will have an exceptionally large number of friends, and virtually no one will be left behind. So effectively, what they said is that if networks are random, at the end of the day, they become very uniform. That is that we will all have roughly the same number of friends. Each node will have roughly the same number of links. One way to put it, that if we assume that networks form randomly in the same way as Erdős and Rényi described, and the society really would be a random network, then, if you look on your left and you look on your right, the person on your left and your right will have roughly the same number of friends as you do. There will be no outliers. No one will become hugely popular. And as I said, no one is left behind. So this is 1959. And, we don't call this network science. We call this graph theory, random graphs. Beautiful body of work, by the way. And what I actually did much of my life is that, with due respect to Erdős and Rényi, who are my countrymen, what we showed in network science that This is all wrong. And the reason it's wrong is because networks are not random. There's no network out there that would be random. But networks have deep organizing principles. And many different networks are very much alike, despite of the nodes are being different, the links being different. So what I'm going to do now is that we'll start from here, and we'll tell you how real networks look like. All right? And our first insight back then came from looking at the World Wide Web. Why the World Wide Web? Well, we wanted to find a network that we could really map out. And the web is a public entity, so we could actually map it out. And the web is a network because the nodes are the documents and the links are the URLs, the things that you can click to go from one page to the other, right? So the name already said it's a network, it's a web, right? And it's a huge network, had more than 1 trillion documents, has now more than 1 trillion documents. Back then was of the order of magnitude of 800 million when we started this research. And you could just simply go to any web page and find the links on that and go to those and find the links on that, and you could get a map like that. It would be terribly boring to do so. So instead you write a code, which is called typically a robot or a crawler, which does it for you, that goes to a web page and finds all the links and then goes to those pages and finds all the links and step by step returns a map of the web. Like nodes are the web pages, links tell you where can you go with one click from that. This is not a magic. This is what actually Google has been doing about the same time. So Google was founded roughly about the same time when we were doing that, this mapping of the World Wide Web. And that's exactly what they did. There were only two differences between what Google did and what we were doing at the same time. First, we only cared about the links. We cared only about the network. So we never kept the content of the pages, right? What was written except where you could go from there. So that's the first difference. The second difference is a couple of $100 billion as a result. So down the line, actually, we ended up getting a map of the world, a certain region of the World Wide Web, and we said, well, the web should be like a random network, right? Because what you put on your web page reflects your personal interest. If you care about cocktails, you'll put lots of cocktail recipes, right? If you care about art, you may connect to Picasso or Duchamp or something else. If you care about sumo wrestling, you will do yet another set of slides, right? So, and since I cannot really predict what your interest is, if I pick any of you, it's going to be completely random from my perspective where you're going to connect. And as a result, you know, we could assume that the network would be random. The World Wide Web should be random, which means if I count how many pages each web page has, it should follow this Poisson distribution as Erdős have predicted. And we did that measurement, and we found something different. So we found a different function. This is what we call a log-log plot, and this is kind of the function that we found. Now, you don't need to know actually much math to really realize that this is very different. Of course, if you do know math, then you realize that this is a very different animal from that, right? But that by itself would be really exciting for a couple of mathematicians and physicists that we found a different function than what we expected. Let me tell you why it matters that we found a different function. Because the random network would be a little bit look like the highway system of US or Europe, where the cities are the nodes and the links are the highways between them. Why so? Because each city has 2 or 3 or maybe 4 highways connecting it to the highway system. You don't find any major city that would have 100 highways converging to it. It doesn't make sense. That's not the way you build highways. And most cities, actually, most large cities, are connected to the highway system. So at the end, if you were to do a histogram of how many highways each city has, would be probably peaked around 2 or 3 and decays very fast. There are no hubs in that process. However, the function we found for the World Wide Web didn't look like that. It looked much more like the airline system of Europe or US, where the nodes are the airports, and the links tell you where you can fly directly from one place to another one. And each of you have taken a flight, have seen these maps at the back of the magazine, right? And we know that they're very different from that, because here you have lots of tiny airports, and they all connect to a few major hubs, right? And that's what this function was telling us. It was telling us that on the World Wide Web, there are the vast majority of the pages have only 1 or 2 links. That's where the mass of the World Wide Web is. The vast majority of the pages, and when I mean vast, it's really the vast majority of the pages no one cares about, right? There's only 1 or 2 links pointing to them. And then there are a few pages that have hundreds of millions of links, like Google, like Facebook, like Yahoo, like Amazon, and so on. So it's hugely uneven. It's not like, hey, we are all alike, and look on your left and you look on the right, and you will find people just like you. But rather, you look on your left and you look on the right, and you see mostly small guys. And occasionally, you will find one that is huge, that is like orders of magnitude bigger than everyone else, right? So that's what this kind of measurement was showing us on the World Wide Web, that the World Wide Web is terribly uneven. So we ended up calling these type of networks where there's such an unevenness, such an inhomogeneity, that there are many, many tiny nodes are connected by a few major hubs. We end up calling them scale-free networks. But if all you need to remember whenever I mention a scale-free network is that it's a network where a few major hubs hold together many, many tiny nodes. Now, fine. We found that the World Wide Web happens to have that property. Why do we care, right? Well, one next interesting thing was the realization that it's not only the World Wide Web, and maybe not only the airline system, but there are other systems around us who happen to, other networks around us who happen to have a very similar property. Let's look at an organization. So this is actually, let me tell you a story about this data. So I want to talk about the networks that we're part of. And all of you probably have a job, either as a student or as a working somewhere. And so we're part of organizations. And this is actually all the employees of a particular company in Hungary, kind of a mid-sized to small company, about 300 employees, whom they turned to us a few years ago because they wanted to solve, the management wanted to solve a problem. Their problem was that every time the management made a decision, somehow the news were not getting to the workers. It was worse than that. What they realized is that often the workers had completely the opposite in mind than what the management had in mind. So any of you who really works in a large organization knows that feeling, right? But down the line, they came to us and said, could you help us figure out what's going on? Why are we not able to communicate what we want to the employees? We do everything right. And they actually hired first an HR firm, and they did some questionnaires, and they confirmed that the management is correct. The workers have no clue what the management wants. So what we did is that we turned these employees into a network by simply going to each of them and say, can you tell me whom do you talk on a daily basis within your organization? Can you tell me whom do you turn to when you have a question about organizational matters? Where do you get your jobs from? Where do you delegate your jobs? That is, like, who is your boss and who are you boss of, right? And what this ended up doing is turn this list of employees into a network, where the nodes are the same employees that you saw earlier, but the node size now corresponds to how many links they have. Now, you see that there are many, many small individuals, like hardly any links, and there are a few major hubs here as well. And those are not big because they think very highly of themselves. They're big because lots of other people pointed to them as saying, they are the person I would turn to. They are the person I talk to on a daily basis. They are the person, if I have a question, I would go to have that answered. So from the perspective of networks, what we see is that these hubs are present within our organization as well, right? Within our universities, within our schools. And we all kind of sense who they are, sometimes, but often we have no clue. And of course, the question is, why did this company have this problem that the news were not getting to the employees in the right way? And I'm afraid that you have to stay till the end of the talk to find the answer to that. And it has to do with these hubs, obviously. But what I want you to kind of remember is these hubs are all around us in the organizations that we're part of. And these hubs are part of communication networks. This is the map of the internet about 10 years ago. Nodes are routers. Links are the physical links. I know in many people's mind, the World Wide Web and the internet kind of live in the same space, but they're really very different animals, right? The World Wide Web is this information network where web pages, information connects to each other. The internet is the infrastructure, the cables that allow you to send messages and to read a web page. So this is really hardware. But what you see on this map, that there are a couple of major hubs that hold many, many small nodes together. So the internet is actually a skill-free network. We know that since 1999, when Falutsos have written a basic paper showing that the internet structure is also a skill-free network. So we see it on the internet, we see it in organizations. Let me tell you a fun example. How many of you have heard of the Kevin Bacon game here? All right, about 1/3. So for the rest of you, let me tell you this story. So this is actually what used to be in the 1990s a very popular game, and the game went like that. If two people are playing, one of them would say an actor like Tom Cruise, and you had to connect Tom Cruise to Kevin Bacon through the movies in which they played together. So if you were good at movies, you would say, well, Few Good Men, and they played together. So therefore, Tom Cruise is one link away from Kevin Bacon, or in the terms of the game, he has Bacon number 1, right? But sometimes you could give more difficult problems, right? So you could say Austin Powers. Well, Austin Powers never really played with Kevin Bacon, but he played with Robert Wagner. And who played with Kevin Bacon? So what's his Bacon number? There you are. And what is interesting about this game is that you can take such a historical actors like Marilyn Monroe and Charlie Chaplin, and they would have Bacon number 2 or 3. So at the end of the day, you would find that just about anybody within Hollywood could be easily connected to Kevin Bacon. Now you would ask, why Kevin Bacon, and why is that possible? Once again, you still have to wait for the end of the talk to find the answer to that. But it turns out that this came up in the 1990s, but it was not invented then, right? It was actually invented in the 1970s by who else but mathematicians. So what mathematicians realized is that Erdős was no ordinary mathematician, but he collaborated with just about everyone. So they started to actually calculate how far they are from Erdős. So a mathematician would get Erdős number 1 if they wrote a paper with Paul Erdős. And about 505 individuals in the mathematics had that honor of having Erdős number 1. If you wrote a paper with someone who wrote a paper with Paul Erdős, your Erdős number was 2, and you can figure out the rest, right? And it turned out that even people who had nothing to do with mathematics, like Einstein or Paul Samuelson, the economist, had Erdős number 4 or 5. So just about which kind of showed how interconnected science is in general. You don't have to work in the same field to find a path between two randomly chosen scientists through various collaborations. Now, one of my big sadness in life is that I have a much shorter Bacon number than Erdős number. And that is because my Erdős number is 3, because I wrote a paper with my advisor, Tamás Vicek, who wrote a paper with László Lovász, who wrote a paper with Erdős. And my Bacon number is 1, because there was a documentary on network science where if you look at imdb.com, which is the official source of such an information, you would find that the first actor in the movie is Kevin Bacon playing himself. And the second actor is László Barabási playing again himself. So, and at any moment, I would love to give up my low Bacon number for a low Erdős number, but as you can figure out, that's not possible since Erdős passed away a few years ago. So, why can we play the Kevin Bacon game? Why do we have a small Erdős number, most scientists? That's because both the scientific community and the acting community form very small professional networks, right? And that we're all part of the same network through our collaborations, and the path lengths between the individuals is relatively short between them. So And if you go ahead and analyze both the mathematics community or the physicist community or the biologists or the actors, you will find that there are a scale-free network. That it means that there are a few major hubs that connect the whole community together, like Erdős or potentially Kevin Bacon. And the vast majority of the actors are those whose name you don't remember because you typically walk out of the theater before their name slowly comes down the screen. So that's really where most of them are, and therefore, there's this huge inhomogeneity in this community as well. Now, all the examples I've given so far have to do with networks that we built, right? Internet, actor network, the scientific collaboration network, and so on. So this is kind of suggesting that maybe hubs are due to something that we humans like to do, right? We somehow like to create hubs. We want to have famous individuals. We want people that everybody turns to, and so on. Well, is this so? Well, to answer whether this is something that we like to do, we have to find a network that we did not explicitly build ourselves. And there are networks like that out there. And those are typically within our cells, right? The metabolic network or the protein interaction network. What is this network? Well, each of you who actually had a cocktail, now you probably feel very happy and very excited about science, right? And the reason you do so is not because your cells can recognize the concept of a Bloody Mary or whatever you got up there, but they only recognize that food in terms of the chemicals that get into your body. And this is the network, the metabolic network, that takes that Bloody Mary and turns into something that your cells can recognize. It breaks it down into the components that the cells like, which is ATP, ADP, and many other small molecules. So that's your metabolic network. This is the protein interaction network, that big blue one that I showed you at the beginning, telling us how proteins connect to each other by gluing to each other and getting something done together in the cell. Both of these networks, it's harder to see here, but it's obvious there, they are dominated by hubs. There's one hub here, there's one there, there's one down there, and so on, and there are many peripheral nodes. So, and indeed, if you do the analysis mathematically, you find that these are also scale-free networks, which, if you think about it, it's pretty amazing. Because let's stop for a moment and understand what we actually saw here. What we saw is that the network that we humans built 25 years ago, and we called the World Wide Web, has the same underlying mathematics and architecture as the network that life built over 8 billion years, right? So it has the same hubs. It has the same number of large and small nodes existing together. It follows exactly the same mathematical rules, which raises a really interesting question. Why is this common architecture? How is it possible that this network is so similar to the World Wide Web or to the internet or to the organization network that we create day by interacting with our colleagues? And on the technical terms, the question we need to ask, what's wrong with the random network model? Why is it not telling us about the hubs? Why are hubs missing from those? And that was really the question that we asked in 1999, as soon as after the World Wide Web told us that networks are not uniform, that they're not random. So then explicitly the question was, what's wrong with the model of Erdős and Rényi? Let me walk you through that. It's very, very briefly. So the random network model has two assumptions that are fundamental to the model, and they turn out to be wrong. The first one has to do with the fact that what the model wants you is that you put a bunch of nodes down there and somehow you connect them. That is, you as a modeler, your role is to figure out how to connect. How do I put links between you in this room, right? That's my role. But in real networks, the number of nodes is not fixed. It's not that you guys come together and start becoming friends. It's more like the networks grow by adding one node at a time. Think of the World Wide Web. In 1991, we had only one web page, Tim Berners-Lee's first web page at CERN at Geneva. And then we have more than 1 trillion today. How did we go from 1 to 1 trillion? Well, one web page at a time. Each of you coming of age and saying, I gotta have my web page, I gotta put my stuff out, and adding new links to it. So if you think about it, the World Wide Web and most other networks have really emerged, one node at a time, always adding new nodes. That is, they are not static. Rather, if you want to model them, you start with a small core, the first nodes, and you keep adding new nodes to it, one, another, and so on. So this is really the first key ingredient of most real networks. There is no large network that would just pop up with 1 million nodes. They all emerged one node at a time, joining the previous network. Now, fine, I have a new node here. How do I decide how it's going to connect, which node it will choose to connect, whom it's going to be friends with, what web page will link to? And again, Erdős and Rényi gave us a very simple recipe. Choose randomly. Any of these people who are there could actually be your friends. Any web page is a potential target for you. But I would argue that that's again incorrect. Rather, new web pages tend to connect to the more highly connected nodes. And not that's because they like the more connected nodes, but because that's what they find. That's easier to find. So if you think about the World Wide Web, you know, how many web pages do you know personally? At most a few hundred. Well, which are the web pages that you know? Well, you all know Google and Yahoo and Facebook and so on. And maybe you know a few hundred other web pages, but as a group, their criteria is that they're typically well-known web pages, because the well-known web pages are easy to find. So we connect to what we know, but we tend to know the more connected pages. And this is what we call mathematically preferential attachment, which means that I can connect to any node here, but I'm biased towards the more connected nodes, and the likelihood that I will connect to one of you is proportional to how many friends you already have. The likelihood that I connect to one of your web pages, the likelihood that I find one of your web pages is proportional to how many other people point to it in the first place. If no one points to it, it's impossible to find it. So this is what we call preferential attachment, and it says, yeah, you can connect to that guy, and you can connect to that guy, but you are just twice as likely to connect to that guy than to that. So now we have two simple rules, growth and preferential attachment, and we put it together, and you will see a nice network emerging as a result, and you will see that some of the nodes will run away and become very large. They'll turn into hubs. And the reason for that is very simple. There is a rich get richer phenomena taking place in this network. If one node has many more nodes than the other, when the new nodes come in, they're much more likely to find the big guy than the small one, right? So they're more likely to connect to the big guy than the small one, and as a result, the big node will grow faster. And indeed, if you run this network, you will find that you will grow a large network, and you will find that this will actually be a scale-free network with roughly the same characteristics as the World Wide Web. So one of the things we learned in the last 15 years is that lots of things happened in networks. Nodes could disappear, links could disappear, links could be rewired, nodes could change their character, and so on. But as long as the networks that we have in front of us are the result of some kind of growth process, and there is preferential attachment there, then hubs will inevitably arrive. And then networks will turn into scale-free networks. So the reason why so many different networks have this common scale-free architecture has to do with the fact that they're all the result of this growth process, some kind of growth process. Sometimes it takes 4 billion years to grow the network, like the networks within ourselves. Sometimes it takes 25, like the World Wide Web, right? But it is a growth process. And what we find by looking at the data, there is always preferential attachment, that we don't connect randomly. We prefer to connect to the more connected nodes. So that's really the explanation. That's why we have this common architecture, because there are these common rules that describe the emergence of these networks. So now we know why we have hubs. We still don't know why it matters, right? So what if we have hubs? Why do we care about that? And so what I'm going to do in the next few slides is to talk about the fact that hubs matter. They are not just a statistical anomaly that nodes that run away with too many friends and they're too popular and so on, but once they're part of the network, they fundamentally change the way the network behaves. So let me start with one example of how do we see that. Let's talk about the robustness problem. What is the robustness problem? Well, many systems, many natural systems have this amazing ability to be able to function even when some of the nodes are broken. Like when I'm giving this talk, there are probably millions of errors within hundreds of millions of my cells. And yet, luckily, I don't notice that, right? And somehow my cells are able to carry on despite the fact that some molecule hasn't arrived where it's supposed to arrive. Some gene wasn't turned on when it's supposed to be turned on, and so on. So the network was not functioning right. In the same way, on the internet, there are measurements telling us that at any moment, there are hundreds of routers who are broken. They could be fixed in 5 minutes. They maybe will take 2 days to fix it. But at any moment, if you scan the routers, you will find hundreds that are not working. Despite that, the internet is not crashing, right? So the question is, why are these real networks able to carry on their functions when a fraction of their nodes are not functional? And why is it that we design devices like these laptops that just about anything breaks, you can pretty much throw it out. You can't even fix it these days. So why is it that human designs are not robust to lots of failures, but these natural designs that are around us, natural systems, are so? So it turns out that one of the answers has to do with the network. So let's think about it. How would we develop a network perspective of robustness? Well, here's one way to do that. We start with a bunch of nodes and ask the question, what happens if these networks, if some of the nodes break? And this is what could happen. If these 3 nodes break, the network will break into disconnected components. And this may be okay, but most of the time, this probably would be a kiss of death to this particular network, right? Because it's not connected, so you're not able to get from there to there. You cannot communicate to whatever it is. Chemical reactions cannot take place, and so on. So the question is, in general, what happens if I give you a very large network and I start randomly knocking out nodes? And the answer to that actually emerged in the 1960s as well, also from mathematics and physics. And what we learned from that is that if you take a large regular network, like a square lattice, like your math copybook, right? Or you take a large random network, like the type Erdős and Rényi envisioned, they behave alike in the following sense. If you start randomly knocking out a bunch of nodes, at the beginning, it doesn't matter, because if you knock 10 or 20 nodes out, there will be still other ways to get around them, because the network will be still connected. But what they also showed us is that every network has a critical point. And if the number of errors you make in the network is approaching that critical point, then there will be, at that critical point, the network will fall apart suddenly. So it's kind of the reverse of what Erdős has discovered. Erdős had discovered is that if you're trying to build a network, first you don't have one, and suddenly you have one. And the reverse is also true, that if you're randomly knocking out nodes, for a while it doesn't matter, but there will be this critical point when suddenly, from one second to the other one, the whole network will be shattered into pieces. So effectively, the theory says small level of errors is not a problem, but when your level of errors approaches the critical point, you gotta watch it because the network will break apart. Now, this is again all perfectly true, proven mathematically for random networks and for regular networks. It's not true for scale-free networks. And let me show you how is it not true. Let's start with this network that we built earlier, and let's start randomly removing the nodes. And you see what happens is that because there are so many small nodes in the network and so few hubs, your chance of actually knocking out the hub is close to 0. Like if you start randomly closing the airports around the United States or Europe, most airports are tiny, so you will actually shrink your network, but you will not necessarily destroy it. So this is what will happen, what you see here. The network is getting smaller and smaller, but it doesn't want to break apart. And this is not only in this particular simulation. We actually can prove it, that if you have a large scale-free network, and you randomly choose whom you knock out, what you will find is that the network will shrink, but at the point it will actually break apart, it will be pretty much close to 1 when you removed all the nodes. So scale-free networks will simply not break apart by random node removal. They have this extreme robustness built into that, and that extreme robustness comes from the existence of the hubs. Your chance of hitting a hub is very low. Even if you hit one of them, there are several hubs, so the others will keep the network together, and eventually you will shrink the network before you destroy it. But there's a price you pay for that. The price is that what if I'm going to attack the network? That is, I start with the biggest node, and I remove it. And then I start with the next biggest node, then the next biggest node, and so on. And because the network depends so much on the existence of these big hubs, if I really know how the network looks like, I destroy it in no time. Let's go ahead and compare these two networks. We started from the same underlying structure, but here I removed 35 nodes randomly, and here I removed 10 nodes in an attack way. And after 35 nodes, this is still sticking together, and after 10 nodes, this is broken into tiny pieces. This is what we call the Achilles heel of scale-free networks, meaning they're very robust to random failures, but they're extremely fragile to attacks. That is, randomness will not destroy it, but if you know how the network looks like, you can design a strategy to very easily destroy the network. This could be good news or bad news, depending on what system you look at it. From the internet is good news. The robustness is good news because it tells us random router failures will not destroy the internet. The bad news, attacks could. For cell biology, this is all good news because it tells us that random failures will not necessarily destroy a cell, but you could design strategies to kill bacteria or cancer cells if you know the underlying network and you design the drugs to attack the hubs. So one of the things we learn from that is really the hubs really matter. They turn these networks very robust, but at the same time, they turn it very fragile to attacks. And it's not only in this context. We see this property actually in many other systems as well. For example, how viruses are spreading and so on. The hubs really play a major role in that process. Slowly, we're running out of time, so let me actually tell you about some work that we're doing right now, which is just as fascinating as some of these earliest ones, which has to do with the question, how do we control a network? And of course, the question is, what do we mean by controlling a network? Is it means like you want to control a network like a drone, that you make it do things that may not want to do, but you make it do it? Or you actually mean like social control, right? I grew up in Eastern Europe, in Romania, and then eventually I lived in Hungary. And so, myself and probably many others in the audience are pretty scared of the idea of social control, right? So what do we mean by control? Well, let me give you the engineer's perspective of what the control means. Look at a typical car. A typical car has about 6,000 components. But yet, when you drive a car, you don't think about 6,000 components because you can control the car by 3 or 4 components depending on which side of the ocean you are, which is the steering wheel, the gas pedal, the brake, and the clutch if you need one, right? Here you do need one. So, and the reason why you can actually control the motion, the speed, the direction of the car from these 4 components is because the car has been engineered to be controllable by these 4 components. So much so that I urge you never to buy a car that would not have that controllability property, right? But what if I invert the question? What if I show you this map and say, this is the wiring diagram of a car? Could you tell me which are the points from which you can control this network? And unless you are an engineer who actually works with cars, you would be completely clueless. And you would say, why would you ever actually bother asking this question? Because the engineers could answer the question right away. But I would say there are lots of systems where this is really the fundamental and the essential question. Think about what cell biologists do day by day, what medical researchers do. They try to figure out what controls certain processes in the cell so that we can fix it, so we can cure a disease, meaning that, how is the cell controlling it, what it does? A few years ago, the Nobel Prize was given to a Japanese researcher in medicine who discovered 4 genes whose state, if you changed, you can change actually, if you turn them on and off in the right way, you can make a normal cell into a stem cell or a stem cell into a normal cell. What did he discover? He discovered the 4 control points of the normal to the stem cell transition, right? And if you kind of in charge of an organization, so tomorrow you are actually told that here is your company organization and you're going to be the leader of that. You know, what would you do? Well, you would have to figure out who are the people you can rely on to actually exercise your vision. We don't call that control. We call that leadership, right? But fundamentally, what you're trying to do is to figure out what are the nodes that you can rely on, what are the individuals you can rely on to make that change possible, what you want to do in your organization, right? So we went after this question a few years ago saying how you control a network. And we asked that very question. If you give me a question, a network, could I figure out what are the control points? And I'm going to illustrate the answer on this network. You remember, this is the organizational network. And what I'm going to show you now is the networks, the nodes who are not control points, right? All of these vibrating nodes are those that play no role in controlling the network. That is, if you are driving that organization from there, you could not actually achieve change. But, and the reason I'm showing you that the vast majority of nodes are in that category. There are, however, a few nodes who have a control position in the network, that their position is such that through them you can really influence the network. So this is just kind of give you a sense of like, we can really take these tools far away if we know the dynamics of the network as well to ask questions, how would you control it, and so on. So at the end, I think I owe you answers to 2 questions that I raised during the talk, right? The first one has to do with this very organization. Like, why did the management have that problem, right? Why were not getting the news and the memos to the right people in the organization? Why did people have the opposite perception than the management about what's the future of the organization? So as I said, we tried to answer that question by looking at the network of who's talking with whom, who is listening to whom within the organization. And we found these hubs. And there's nothing surprising about these hubs, right? Because they're present in all networks, and in any organization, you would expect to have a few individuals whom everybody turns to. Because that's their job to answer questions, right? They're the managers, they're the leaders. Are they? Well, let's find it out. So what we did is that we simply took this map and we put the management on it, right? We colored the nodes. So the red nodes are the directors and the CEO. And unfortunately, there is no hub among them. Well, let's go one level down. The light blue nodes, right? That's the top management. Many more of those than the directors. But you don't see any big node. There's one tiny there. There's one there. These are the top management, right? This is top management, this guy. No. So when you look carefully, you realize that the biggest nodes are coming from the bottom of the organization. This is the biggest node. This is actually, we call it nicely, associate. But it means that he has no really kind of management role whatsoever. So who is that guy, right? Who's that guy and what should we do with him? Because obviously he is the leader, actually, de facto leader in the organization. Everybody listens to him. Well, I can answer the first question very easily because looking simply at the roster of the individuals, and it turns out that this is the fellow who is in charge of the safety issues within the organization. That is, his role is to go from group to group. These are the 3 different locations, the purple, yellow, and the blue guys here, and talk to everyone and make sure that all the safety regulations are properly observed. Happens to be a very talkative individual who picks up information there and drops it off over there. He has links to everyone within the organization except the top management. So, you see what happens. So, what should we do with him, right? In the smaller settings, I asked actually the people, what would be your answer? And then I get, of course, a range of answers. One of them, fire him. Second one, make him the CEO, right? And the third one is the right one, right? What this map has shown you is that there are maybe 5 people who have an exceptional influence within the organization. Everybody turns to them. So have a coffee with them. Tell them what's going on, right? Because through them, you could actually get to the rest of the organization. So the reason I like this example is to show that how important these hidden networks that we don't see. We don't have a dashboard. The CEO doesn't have a dashboard of how these things look like. So down the line, actually, networks provide us a way to see how this is actually happening. So the final 3 slides. And the most important question in network science, right? And I'm sure you were all waiting for that. Why Kevin Bacon? Right? Why are we playing the Kevin Bacon game? I mean, like, is he really such an important actor? Why don't we play the Charlie Chaplin game, or a Kevin Costner game, or a Tom Cruise game, or something like that? So we were puzzled by that, so we ended up actually going and saying, let's see what are the numbers for Kevin Bacon. And this is a few years ago. We turned out that he made about 46 movies, which is nice. He had direct links to 1,800 other actors, right? So those had Bacon number 1, about 1,800. That's a lot, right? If any of you knows more than 1,800 actors, that's pretty good, right? So pretty much everybody has played with him whom you would know today. So the average separation from everybody else was actually 2.79. So anybody in the history of Hollywood from 1890 to today was about 2 or 3 links away from Kevin Bacon. So we said, okay, well, maybe Kevin Bacon is not the most important person. Let's find out who is the most central guy in Hollywood. And one way to do that is to simply look at how many, probably what matters is that how many movies did you play with, right? Because if you played in many more movies, you're going to have links to many other people. So we ended up listing all the actors in Hollywood based on the number of movies they made. And we found this list, and there was no Kevin Bacon on that. But not only that, but we couldn't recognize anyone there. Can you? Anyone recognize this? I'm sorry, that's bad news that you do. Because as you guessed, these are all male porno stars, right? So then we said, okay, that's the wrong hypothesis. Size doesn't always matter, right? So let's go a step further, and maybe what matters is not this, but maybe how far he is from everyone else, right? So we ended up listing actually the actors based on the distance from everyone else. And now we start seeing people that actually we do recognize as actors that we occasionally see in movies. But again, we don't see Kevin Bacon on this list. So we said, okay, well, let's look at the top 20, not there, top 25, not there, top 100, not there, top 500, not there. But then we eventually found him. We found him in position 876. So one way to look at it is to say, if I would build a big network and see who are the hubs, then I would find that the biggest hub is Rod Steiger. He's like kind of the closest to everyone else. Donald Pleasance, Martin Sheen, number 3. And then if you have actually a microscope, then you may find Kevin Bacon somewhere in there. But this has actually a very important message, which is the fact to say, the reason we can play the Kevin Bacon game is because everybody in Hollywood is close to everyone else. And that's really the fundamental property of the network. Some of us have many links, some of us have much fewer links, but we are all close to each other. So any of us could be the center of the network that we are part of. Thank you very much for your attention.